Welcome back to another AP Pre-Calc video. I'm Mr. Hibble. Today we're looking at a Unit 1 review, looking at, more specifically, some free response questions based on the unit. So 4 different problems we'll go through. Here's the first one. We're given a rational function. We need to determine the equations of different things. Before we start to determine equations of stuff, let's just make sure our fraction is as simplified as possible. So I notice the x plus 3's are going to go away, leaving me with the x plus 1 and x minus 2 on top, and just the x minus 1 on bottom. So from there, then, determine the equations of vertical asymptotes. Well, remember, vertical asymptotes are just taking the bottom, setting that equal to 0. Remember, when you do that, you really only need the factors. I don't need just that number of 2 in front. If you do include it, you'd still get the exact same thing, but set it equal to 0 and solve. You should get x equals 1. For B, then, determine all real zeros of R or state that no real zeros exist. Well, remember, real zeros we know are x-intercepts. Real zeros, then, just mean they are real numbers instead of imaginary or complex numbers. Basically, that just means as long as it doesn't have I, some imaginary part, then it is a real zero. So that would be the top equal to 0. There would be 2 different x-intercepts, 2 different zeros in this case. Take both the top, set those equal to 0. Should get -1 and +2 is what it looks like. Since those are x-intercepts, you might need to write those as a coordinate. So you might write that as -1, 0 and 2, 0. That is for part B there. For part C, what it says is we want to determine any y-intercepts of R. One second, I'm going to change the color on this first one so we can see all the different steps in here. So we said that first one was x equals 1. Okay, I'll make sure to change the color for each of these. So looking at C, then, determine any y-intercepts. Remember, a y-intercept occurs when the x values are 0. So if I plug in 0 into each of the x's, see what we get when we simplify it. On the bottom, that'd be 2 times -1, which is just -2. On top, you'd have 4 times 1 times -2, which would give us -8, it looks like. So simplify that, I believe you get 4. With that being said, though, make sure you write that as a coordinate as well. We knew that the x value was 0, and the y value we found is 4, so 0, 4 for a y-intercept. The next one, then, part D, identify any removable discontinuities. Removable discontinuities is just a fancy word for whole. So whatever we canceled, just solve that. We ended up finding that there was a whole at -3. You might want to be able to find the coordinate of the whole as well. So from there, I would take -3, plug that into our simplified form to find the y value. So -3 plus 1. -3 minus 2, -3 minus 1 on bottom. Simplify that real quick as well. The bottom looks like -8 to me. The top would be 4 times -2 times -5. So if you were to multiply that out and simplify it, then I believe that would give you a value of -5. So I believe we have a coordinate then of the whole of -3, -5 there. Okay. Once we have that now, what we can do is look at part E. E just says determine the end behavior as x decreases without bound. Make sure you write it as a limit statement. So we know that we'd have the limit of x decreasing without bound. Remember, without bound is just infinity. Since it's decreasing as well, that's going to be -infinity. of our function r of x, what should that be equal to? Well, if you go off to infinity in either direction, remember these rational functions look something like that. So we just want to know what asymptote is it reaching on the far left in this case. Well, that would be our horizontal asymptote. So when I look at this function, either at the beginning or at the end, it looks like there is a slant asymptote in this case. To find a slant asymptote, you would have to divide out whatever the polynomials are to find that slant asymptote. But we could look at the end behavior of it as well. I know on top I would have 4x squared, and on bottom I would have 2x for the degrees. Divide that out, I know that I would get 2x. Well, the end behavior of 2x, the right side would go up and the left side would go down, because this polynomial then is an odd polynomial and positive. So if I want to talk about the left side then, well, there is no horizontal asymptote. It's going to decrease forever along the slant asymptote, meaning it would go down forever to negative infinity. Let's go ahead, let's look at the next problem. Those are our answers for number 1. This next one then, number 3, we're given some function. We want to talk about all of this different information. So it says the function g is given by this. Notice it is an 8th degree polynomial, and a, b, c are all positive real numbers. Question A then says, it is known that g has 2 real zeros. What is the maximum number of non-real zeros possible for p? Give a reason for your answer. Well, since this is an 8th degree polynomial, we know that there is 8 zeros between real and complex. So in this case, we already have 2 real zeros. So that means we're going to have some sort of imaginary zeros to give us a total of 8 zeros overall. So these are the real ones. These would be the imaginary or complex. And then this would be the total. Well, in this case, there would have to be 6 imaginary or 6 non-real zeros in this case. I'm not necessarily going to write out my rationale for that. You guys did hear it as I was talking through it. So we do know 6 non-real zeros or x-intercepts. Part B says determine the end behaviors of g. Write your answer as a limit. Well, we know that this polynomial is 8th degree. I also know that the leading coefficient is positive because it says a is positive. So that would tell me that both ends go up for our polynomial here. And then from there, we could just go ahead and write both of our limits. The left side we said is going up, and the right side as well we said is going up towards infinity. Part C then. Part C says use the table to determine what would model this the best. Well, look at the changes in your y values and see what's happening there. Let's see if it's a constant rate of change. Let's see if it's a second difference that's constant, stuff like that. Well, 0 to -1, that'd be -1. -1 to -4, you're subtracting 3. Then you're subtracting 5. Then you're subtracting 7. So the first difference is not the same. But if you looked at those second differences, -1 to -3, well, that would be subtracting 2, and then subtracting 2, and subtracting 2. So what we would end up getting then is this should be a quadratic. The reason it's a quadratic is the second difference is constant. Last thing we're asked to do is describe the rate of change on the interval 0 to 4. One thing you could do is find the rate of change, but we could also describe it in the terms of is the rate of change increasing or decreasing. Well, notice the rates. We said the rate was -1, -3, -5, and -7. Notice each of those values is getting more and more negative, meaning the rate of change is decreasing on the interval. Okay, because it gets more and more negative, it is a rate of change decreasing. Remember, that would tell us that our function is actually concave down. Okay? Last two problems to look at for this section. This next one, consider the function f of x equals x cubed on this domain. Now we're just looking at different dilations. So determine the equation obtained by a horizontal dilation by a factor of 0.5 and a horizontal shift 4 units to the right. So for a in this case, we take our function, which is x cubed. We're going to now create g of x based off of that. Realize x is being cubed, so set anything that is affecting x horizontally would be also getting cubed. Okay, it needs to be inside with the x there. Well, for part A, I have a horizontal dilation by a factor of 0.5. So remember, that means I would have a 2 on the inside multiplying with our x. And we also have the shift of 4 units to the right. Remember, though, whenever we have this dilation and this shift on the inside, we need it to be in the factored form. So I'm going to have another set of parentheses now showing that it moves right 4 units, which would be minus 4. That would be our answer for A. Make sure the inside is in factored form. We were not given... You can just create the factored form right away. We didn't need to actually factor it. Just make sure you put it into that factored form initially. B says determine the equation of h of x now obtained by a vertical stretch by a factor of 2 and then reflecting across the y-axis. So h of x now. Make sure we have our x cubed set up as well. So we know there's a vertical stretch. Anything vertical is on the outside and works normally. So I'm just going to multiply by 2 on the outside. And then it's getting reflected across the y-axis. So if you think about that with x cubed, let's say here's my y-axis. X cubed looks something like this. So if I reflect that across the y-axis, it's just going to take everything and kind of move it to the other side to now do this instead. Notice the y values did not change there, right? I didn't move it up or down at all. I just kind of reversed where the x's were. What that tells me is that is a change in the x direction, the horizontal direction. So the negative should be on the inside. C, then find our domain. We already know the domain for f of x is negative 2 to 6. Remember, domain is just something that affects the x values, right? Domain is the x. So all I care about is what is changing the x values in this case. Well, for G, we had a dilation of a factor of 1/2 and 4 units to the right. So I would take my values in the domain, the negative 2, apply that dilation, and make sure we move it right 4 units. So 1/2 times negative 2 plus 4 would give me 3. Do the same thing with the 6, 1/2 times 6, and make sure we move it 4 units right. That would be 7 for our new domain. Same idea with h of x. Figure out what's changing the x values. Well, in this case, we're just making our x values negative is what it looked like. So all I'm going to do there is just change the signs on them. So now negative 6 to 2, make sure it goes smallest to biggest values. Okay, I did not need to multiply by 2 in this case because that vertical stretch was on the outside. That would change the range, not the domain. Last problem to discuss. This one I know a lot of people don't love, but let's break this down. So we know the limit as x goes to infinity. That would be the very far right side of your graph. X is going all the way to the right. We know all the way to the right, my function is going to be equal to 3. So if I go to the very far right side, all the way over to here, my function will be equal to 3. That's a y value. So that means my rational function might go like this or this. We do not know yet, but it will go along that horizontal asymptote which we were given. Now, this next statement says the limit as x goes to negative infinity, so that's the left side of our graph. Our function is now equal to negative 3. So along negative 3 towards the extreme, the outside, my function will do something like this. Again, we don't know if it's top or bottom yet. The next statement says the limit as x approaches 2 from the right. Remember this 2 or that plus means from the right side. So if I approach the x value of 2 from the right, let's look at that. So I'm going to have some asymptote, a vertical asymptote at 2 now. So it looks like these lines, I'm just going to move out of the way for now. We'll figure out which case they are in a moment. Okay, but I have an asymptote now at 2, and on the right side of that asymptote, as I get closer to 2 from the right, my graph is going to go towards infinity. Well, that means my function is going towards infinity. That means my function is going up. So from the right side of 2, my graph goes up. Well, that fills in this other side for me. That means this side must go there along that value of 3. So now if we look at the next statement, it says from the left. Same idea. So the limit as x approaches 2 from the left, our function is going to go towards negative infinity. So now my graph must be going down to get to that negative infinity. Well, what that would look like then is over here, the left of 2, it is going down. So we know if we continued this then, we would make sure it stays along that value of negative 3 on the left side. So we know that we answered each of these 4 statements. The last one then, are we concave up from 2 to infinity? That would be this section of the graph up here. That does look concave up to me. So we would have our final answer sketching this rational function. That is all for the review of the free response questions. Hope that helps you guys prepare for our test.